So in this video, we're going to look at a very important topic in chemical equilibrium. It's referred to as Le Chatelier's principle, named after a French chemist, Le Chatelier. We've been dealing with chemical equilibrium, and we know that equilibrium means that you have a reaction where the forward rate is equal to the reverse rate. So everything in the reaction mixture appears to be constant. Temperature is constant, concentrations are constant, pressures are constant, color is constant. It looks like the reaction has stopped because it's reached equilibrium. Well, Le Chatelier's principle deals with disturbing that equilibrium. So you do something which makes the system no longer at equilibrium. We call that a stress. You're applying a stress or a disturbance to the equilibrium. And Le Chatelier's principle says that if you apply a stress to an equilibrium, the system will shift forwards or backwards in order to reduce that stress. So pause here and record that as a statement of Le Chatelier's principle. A system is at equilibrium. You apply a stress to the system. It's no longer at equilibrium, and as a result, it shifts forwards or backwards to reduce the stress and reach a new equilibrium. Now keep in mind that when we say it shifts forwards, if a reaction shifts forwards, then everything on the left side of that equation would decrease in amount. So you'd have less grams or less moles of anything on the left side of the equation if it's shifting forwards. If it's shifting forwards, anything on the right side of the equation will increase. So you'll have a higher concentration of gases or aqueous species. You'll have more grams, more moles, etc. A reverse shift, the opposite happens. In a reverse shift, things on the left side will increase in amount, while things on the right side will decrease in amount. Now, what are some stresses? How can you disturb an equilibrium? Well, basically, if you think back to our kinetics unit, the factors that affect rates of reaction. At equilibrium, forward and reverse rates are equal. If you do something that changes that, if you do something that makes the forward rate faster, for example, or the reverse rate slower, then that will affect the equilibrium. So things like concentration changes. If you increase the concentration of a reactant or a product, or decrease a concentration. If you change temperature, which we know affects rates, we also remember temperature affects the value of Kc. If there are gases in the container, changing its volume will also affect the equilibrium, because when you change the volume and gases are present, then you're changing the concentration of the gases. But one thing to remember is that if you're adding or removing liquids to the system, or adding or removing solids to the system, then that will have no effect on the equilibrium. Liquids and solids have constant concentrations, so when you add them or remove them, their concentrations don't change. You may have more grams or more moles, but you have the same concentration when you add liquids or solids. Okay? So liquids and solids do not cause equilibrium to shift. However, if the equilibrium does shift, if you do something which causes the equilibrium to shift, then everything in the reaction, liquids, solids, gases, aqueous, they'll all change, right? If you're going to shift forwards, everything on the right-hand side of the equation, you'll get more of that. But if there's liquids and solids present, their concentrations don't change. So here's an example of a reaction. You can pause the video and write that down. You notice that this is a heterogeneous equilibrium. There's a solid present. The product CS2 is solid. Everything else is gas. Now this equation has the word heat written on the left-hand side of the equation. You might want to note for yourself, when the word heat is written on the left like this, then this is an endothermic process. Endothermic. If the heat were written on the right-hand side of the equation as though it were a product, that would then be exothermic. So when heat is on the left, the forward reaction is endothermic. When heat is on the right, the forward reaction is exothermic. You also remember that in an endothermic reaction, the enthalpy change, the heat of reaction, is positive. So that's another way of saying that it's endothermic. The delta H, the heat of reaction for the forward reaction, is positive. You might remember that from our kinetics unit. If the forward reaction has a positive delta H, it's endothermic, then the reverse reaction would have a negative delta H. It would be exothermic. All right. Now the question is asking us to predict what will happen to the amount of SO3 in our container if we perform various stresses. So we're trying to figure out what happens to the amount of SO3 if we perform various stresses. Well, the first thing to notice is that the SO3 is on the left-hand side of our equation. Why do I want to notice that? Well, if it's on the left-hand side, then if a stress causes a forward shift in equilibrium, if the shift is forwards, then the amount of SO3 in the container would decrease. Because if it's shifting forwards, SO3 would be a reactant, and reactants get used up. If the equilibrium were not to shift forwards, but instead shifts reverse, if it shifts backwards to the left, then now the SO3 would be produced. So shifting backwards, the amount of SO3 would increase. All right, so a forward shift would decrease the amount of SO3, while a reverse shift would increase the amount of SO3. So if we want to predict what happens to the amount of SO3 as a result of the stresses down below, we need to figure out, do they cause a forward shift or do they cause a reverse shift? To do that, it would be helpful to write the expression for the reaction quotient. Okay, so let's do that. The reaction quotient, Q, pause the video and see if you can write that expression for Q. Remember that liquids and solids are left out of the expression. So we'll get the concentration of the oxygen, the product on the right, to the power of 4 divided by the concentration of carbon dioxide times the concentration of SO3 squared. There's the expression for the reaction quotient. Now you also remember that when you're initially at equilibrium, Q, the reaction quotient, is equal to Kc. We're initially at equilibrium, so Q and Kc are equal. We know that if you disturb the equilibrium, there'll be a shift in equilibrium. Well, there's one of two possible results. Q might end up being greater than Kc, or Q might end up being less than Kc. If Q is greater than Kc, we know that that causes a reverse shift in equilibrium. If Q is less than Kc, that causes a forward shift in equilibrium. So with that review, let's jump into the first stress. So write that first one down for yourself. We're going to add some carbon dioxide to the container, to the vessel. So look at your expression for Q. If you're adding carbon dioxide, you might want to jot down what I'm saying here, then the concentration of carbon dioxide increases. That's the first thing I would note. The concentration of CO2 increases. The second thing I would note is if carbon dioxide is in the denominator of Q, then a larger value for carbon dioxide's concentration makes Q smaller. So if you're dividing by a larger number, Q will decrease. So adding carbon dioxide causes its concentration to get larger, and that causes Q to get smaller. The third thing you might note is that Kc doesn't change, right? The only thing that can change Kc, the equilibrium constant, is if you change the temperature. So adding carbon dioxide does not change Kc. The fourth thing to note would be that if Q is now smaller, but Kc didn't change, then Q must now be less than Kc. Q is less than Kc. And As we said above, that results in a forward shift of equilibrium. That would be the next thing to say. It's going to shift forwards in response to this. And the last thing to note is that if it's shifting forwards, SO3, which is on the left side of the equation, will decrease. So the amount of SO3 will decrease. So let me go through that one more time. You can make sure you've got each of these things written down, perhaps in point form. So we added some CO2. The first thing I would say is that causes the CO2's concentration to increase. Next, I would say that will cause Q to decrease because we're dividing by a larger number. If Q decreases, I would next say that Kc, the equilibrium constant, did not change because we didn't change the temperature. So the next thing would be that Q must now be less than Kc. And as a result, the reaction shifts forwards, and there will be less SO3 at the new equilibrium. There's a complete, solid answer. All right, so let's try another one. So the next stress, pause and write that down. We're going to add some CS2, the carbon disulfide. All right, so if you start thinking about what we just talked about a moment ago, you look at the expression for Q and you realize CS2 is not in the expression for Q. And it's not there because CS2 was a solid, right? Look back at the balanced equation. It was a solid. And we know that solids have constant concentrations. So this would be my answer. Adding CS2 has no effect on Q because it's not in the expression for Q. It also has no effect on Kc, which means Q is still equal to Kc. Q is still equal to Kc because CS2 had no effect on either one. That means there's no shift in the equilibrium, and that means nothing will happen to the amount of SO3. All right, so CS2 was a solid. The solid doesn't affect equilibrium. It's not in the expression for Q, so Q does not change. Kc doesn't change because the temperature didn't change, so Q and Kc are still equal. And that means there's no shift in equilibrium, and the amount of SO3 will stay the same. Try the third one. Write the stress down in your notes. Oxygen is removed from the container. What will happen to the amount of SO3 as a result of that? All right, so the first thing I would note is that if you're removing oxygen, you're decreasing oxygen's concentration. You're lowering the concentration of oxygen. Next, I would look and see that oxygen is in the numerator of Q. So if you're going to decrease oxygen's concentration, you're decreasing the numerator of a fraction. The numerator, the top of the fraction, is getting smaller. That means Q will get smaller also. If you have less numerator, a smaller numerator, the fraction gets smaller. So removing oxygen causes its concentration to drop, and that will cause Q to also drop because oxygen is in the numerator. If you have a smaller value of Q, you should also note that Kc does not change because the temperature didn't change. Kc stayed the same. So therefore, Q is now less than Kc. If Q is less than Kc, the reaction shifts forwards, and shifting forwards, there will be less SO3 at the new equilibrium. Okay? You can play that explanation again and pause it each time to write it in your notes if you need to. Now, the next stress is different. We're going to suddenly, for the first time, change the temperature in the container. Now, this reaction, we know that temperature affects Kc, and this reaction was endothermic. So I'm going to give you some information that we haven't seen before. We know that Kc changes with temperature, but we don't know how. So take a look at this, and you're going to want to jot this in your notes. If you have an endothermic reaction, then the relationship between Kc and temperature looks something like this. Okay, so what's that telling me? It tells me that as the temperatures get larger, the Kc also gets larger. So when you raise the temperature, Kc gets bigger if it's an endothermic reaction. If you lower the temperature, the Kc gets smaller in an endothermic reaction. Now, if the reaction were exothermic, you should write this down. If it were exothermic, then the relationship is the opposite. So now when you change the temperature, the graph will look like this, which means as you raise the temperature, Kc's get smaller. And as you lower the temperature, Kc's get bigger. So you want to have those two graphs memorized. And when you do a Le Chatelier problem, if you have an endothermic reaction like we have here, you would sketch that graph in your answer. Just like you wrote the expression for Q, you would sketch the graph of the endothermic relationship of Kc and temperature. If the reaction were exothermic, you would sketch the second graph. Okay, so now that we know the relationship between Kc and T, this is an endothermic reaction, so that's our relationship. Let's look at what happened. We're heating the system. Well, heating the system means we're raising the temperature. Raising the temperature has no effect on Q, right? It doesn't affect these concentrations, so Q doesn't change. You should note that. None of the concentrations change, but therefore Q will not change. But now we look at our graph and we see that if you raise the temperature, Kc will get larger. So that's the next thing to say in your answer. Kc will increase when you raise the temperature in an endothermic reaction. Kc gets bigger. So Q did not change, but Kc is now bigger. So that means the next thing to put in your answer would be that Q must be less than Kc. Q didn't change and Kc is now bigger, so Q is less than Kc. And now we're home free. If Q is less than Kc, the reaction will shift forwards. And if it shifts forwards, we'll have less SO3 at the new equilibrium. All right, so far, we've had three stresses that caused forward shifts and therefore less SO3. And we had one situation where there was really no stress. You added the CS2, which was a solid, so it had no effect. So there's a couple more things to note here. The next example talks about the volume of the vessel is reduced by half. So the volume is decreased in the container. Well, if you decrease the volume of a container, that will increase all of the concentrations in the container. You remember that concentration is equal to moles divided by volume. So if you reduce the volume, if you have a smaller volume, you're going to have a bigger concentration for any of the gases. So looking at my expression for Q, the concentration of oxygen will go up. The concentration of SO3 will go up. The concentration of CO2 will go up. All of those concentrations go up. So what happens to Q? Well, this is a bit more complicated. So take a look at the exponents in Q. In the numerator, the exponent is a 4. So if this were a kinetics unit, if you remember the rate laws we talked about, we could say that that's fourth order overall. The denominator, the bottom of Q, has a 1 as an exponent for CO2 and a 2 as an exponent for SO3. So 1 plus 2, the denominator is third order. All right? Now, both the numerator and denominator are getting larger. However, the numerator has a larger order. It's fourth order. That's larger than third order. So that tells me that the numerator will get even larger. So while both the top and bottom increase, the top increases even more because it's got a higher order. So if it's going to increase even more, then Q will get larger. You have a larger numerator, Q will get larger. So there's what you want to note. Let me go back. Reducing the volume causes all of the concentrations to increase. The top and bottom of Q will increase. But because the numerator has a larger order, the numerator will increase more than the denominator. And that causes Q to get bigger. Kc did not change because the temperature wasn't changed. So if Q got bigger and temperature wasn't changed, so Kc stayed the same, that means Q is now larger than Kc. If Q is larger than Kc, this reaction will shift backwards as a result. Shifting backwards is going to produce more SO3, so the amount of SO3 will increase. Okay, and then the next stress, the next apparent stress, is to add a catalyst. What happens if you add a catalyst? Well, this is a simpler one. If you add a catalyst, look at the expression for Q. The catalyst isn't in the expression for Q, so the catalyst has no effect on Q. You should note that. Q does not change. None of the concentrations in Q will change with the presence of a catalyst. So that means Q is constant. Well, Kc also doesn't change because you didn't change the temperature. So Q didn't change, Kc didn't change. So that means Q is still equal to Kc. Q and K are still equal. If they're still equal, there's no shift in the equilibrium and nothing happens to the SO3. So the catalyst has no effect on the equilibrium. Remember, the catalyst speeds up the forward and reverse reactions, but it speeds them up equally. So while the two rates were equal to begin with, it was at equilibrium, adding the catalyst makes the forward and reverse rates faster, but they get faster equally, which means there's no shift in equilibrium. And finally, we have a gas, like a noble gas on the periodic table, the last column, helium, neon, argon, those elements on the far right-hand side of the periodic table, those are noble gases, and they generally don't react with anything, especially the elements at the top, so helium won't react with anything. So we're taking a gas which is unreactive, and we're adding it to our flask. Now, this could be a complicated situation, but in our situation, we have a rigid vessel. If it's a rigid vessel, that tells me that the volume of the container won't change when we add the helium. Rigid means it's solid, it doesn't change. So adding the helium doesn't change the volume in the container. If it doesn't change the volume, then none of these concentrations in Q would be changed. So adding helium, it adds another gas to the container, but it doesn't change any of the concentrations of the gases that were there to begin with. So the oxygen, the CO2, and the SO3, their concentrations are not changed. That means Q is not changed. So adding helium, an extra gas, doesn't change Q. Of course, it doesn't change the temperature, so Kc is also unaffected. So Q and Kc don't change. We've seen this a couple of times. That means Q and Kc are still equal, and that means there's no shift in equilibrium and nothing happens to the amount of SO3. All right? So I hope, this is a complicated topic, Le Chatelier's principle. I hope as I explained those things, you paused the video and wrote down some good explanations in your notes, okay? I'll post another video on Le Chatelier's principle tomorrow where you can practice and check your understanding.